Welcome, welcome. Thank you all for getting your notes ready. Thank you for getting ready to go. I look forward to seeing y'all tomorrow, but we gotta get this going. Today we're actually gonna be taking notes on both sides, so it's gonna be a little bit more, it's gonna be a little bit different than what it normally is. So bear with me, stick with me. It will be in color, so you need your pencil and some colored pencils. I may use some colored pens. If you have colored pens or markers, that's fine as well. Color is pretty important on these notes because this is heat, and with heat we talk hot and cold, and so red and blue, those are kind of important things. So let's go. So first up, we're going to take your notes page on this side, and we're going to divide the page in half diagonally, which means across. I've got a ruler. You don't have to have a ruler. It can just be a line. It's no big deal. It's not art class. Remember, things don't have to be perfect. Along this line, we're going to start out real simple, and we're going to start out with our definition of heat. So heat is the kinetic energy. What does kinetic mean? Kinetic means moving around. So heat is the kinetic energy of molecules and atoms. And just as a side note, we're going to put movement, because heat really just measures how fast molecules are moving around. So here we go. Here's some picture drawings. So first we're going to do radiation. Y'all remember from the board, which is, I want to say it's going to be right over there still, the conduction, the convection, and the radiation. You know that radiation, the key word is empty space. And so we'll start with the sun. So I'm going to draw the sun, because the sun is a perfect example of radiation, because what's around the sun? Nada. The sun just has empty space around it. So when heat travels away from the sun, it does so in waves, and those waves are what make it radiation. So I'm going to try to be fancy. This is radiation. Waves. So radiation travels in waves. If you want to be even more fancy, we can do radiation. Because it travels through space. It doesn't need anything. There's no air, there's no liquid, there's no solid in space. It doesn't need anything. So you have heat traveling. Heat. So some other examples of radiation. We need a little earth, don't we? A little bit of earth. And on earth we've got land. Look, this is not art class. Clearly this is not art class, because I'm not an artist. I'm just drawing things. So we have our earth, and this is how heat gets to earth from the sun. A couple of other examples. Another example is a light bulb, like an old-fashioned light bulb. So not like LED lights, because LED lights don't get real hot at all. So these light bulbs in the olden days, these light bulbs would have this little filament inside, and this little filament would glow, and that would radiate heat. And so that would radiate heat all around the light bulb. heat. Now, you don't have to touch the light bulb. There's no air blowing around the light bulb. It is just heat going away from the light bulb. And this heat going away from the light bulb is still traveling in waves. The other big example, and this is one that I almost guarantee you they're going to put on a test when we take a test or whatever. I think we're taking a test in February. From the district, but they put this one on the test every time because it's kind of an example of all three methods of heat transfer or thermal energy transfer. But this one, some of you may know, not everybody, because not everybody goes camping. Not everybody has a fire that they've been around. But a fire demonstrates radiation really well because when you stand next to the fire, you get warm. And in fact, that is why we make a fire, is to be warm. If you've ever roasted marshmallows over the fire, you know that they can cook. But you also know that if you touch the fire, it burns your marshmallow. And we know that touching is not radiation. Touching is, look over there, touching is conduction. So that actually is where we head next. Next we will be, we'll do conduction. Conduction is pretty, I'm going to do it with a pencil this time, not an ink pen. Conduction is pretty interesting because conduction can only happen when you touch. You guys know this. You practiced this in the lab already. So I'm going to do some block letters. Good luck. If you can't do block letters, you don't have to do the block letters because, oh, I just messed up that one, didn't I? Yeah, block letters can be hard, clearly, but conduction requires direct contact. So that D, you know what? I'm going to color it in different because that is important. So that's direct. And there's our C. So the C direct contact. Kind of regret doing block letters right now. That's an O. Conduction. Conduction relies on direct contact. And direct contact means touch. Note, if you don't touch it, you can't have conduction. So yesterday in the lab, y'all did a thing with the ice. And the ice you put, I'm terrible at drawing hands. Whoa, these are long fingers. Leave my fingers alone. In the lab yesterday, you had ice, and you put that ice in your hand. And as you held the ice in your hand, oh God, that hand is horrible. As you put that ice in your hand, I'm going to draw a little block of ice real quick. What happened to the ice? The ice, it kind of made a mess because in your hand, the ice melted. And that ice melted because you were touching it. On one of the questions on the lab asked you, did the heat from your hand go to the ice, or did the heat from the ice go to your hand? So which direction was that transfer? You're going to find out tomorrow. Tomorrow we're going to do another little doodle notes, and that doodle note will be all about ice, hot versus cold. But heat always moves hot to cold. hot to cold. So your hand is warmer than the ice. So the heat from your hand went to the ice, and that's what melted the ice. The ice technically didn't make your hand cold. Your hand made the ice warm. So another place that we have conduction, and forgive me because this is going to be another moment where Mr. Harris cannot draw. Drawing a little pot like you would put on the stove. And if you have an electric stove, underneath the pot, oftentimes you'll see something that glows. And it's a little coil. And that coil touches. So that coil is touching. The coil is touching. So that touch means that it is conduction. So one last example, and this is one that not everybody is going to recognize possibly. It is a breakfast thing. It is tasty. Some people don't like them, but I love waffles. So a waffle iron, what makes a waffle different and special compared to a pancake is that the waffle has that neat texture. And that texture is cooked into the waffle because the waffle iron does what? The waffle iron touches. The waffle iron touches. So the waffle iron has conduction. So this is the plug. Yeah, it's a terrible plug. But the waffle iron is touching. So again, touching. So conduction requires direct contact or touch. If your item is not touching, you cannot have conduction. It's easy as that. So radiation, conduction, and that leaves us one thing. And then that one thing is convection. So convection is movement. Convection is mixing. So convection is always about currents. And as such, we're going to look at currents. I drew this on the board the day that we took notes. This isn't entirely new. I need my blues, I need my reds. So convection currents. Get all my stuff. So at the top of my page, I'm going to write convection. But I'm going to do something a little different with my O's. Because with my O's, I'm going to make them pretty because in convection, we have movement. And that movement always moves in the same way. Warm air or warm water or warm magma rises and goes up, and as it cools, it will fall back down. So convection. Several things going on this page for convection. We're going to fill this up probably. So let's do this. First, I drew this on the board. So convection, you have warm, and warm goes up, and as warm starts to cool off, it'll turn and level out because it wants to start falling. So the air will cool off, and cool air falls, or cool water, or cool anything. Cool goes down. And then when it gets to the bottom, it starts over where the cool will start to warm up. And once it's warm, it will rise again. You know what? Color pencil would be faster. And this movement is convection. So this movement causes a mixing. Mix or move. So warm rises. Cool sinks. And this mixes everything. And this mixing, if the mixing is in the air around you, we call it wind in the air. If this mixing happens in the oceans, the water mixes, that is an ocean current. Or if it's in the earth, like underground, in the earth, under crust, so deep underground, the magma will also move and have currents. Magma is going to be important because we're going to come back to that. Just a little tidbit, magma and lava are not the same thing. They're both melted rock, but they are very different. As I like to say, you can never be killed by magma, because magma is melted rock underground, lava is melted rock above ground. So you can die by lava, but you can't die by magma. So let's do just a few examples of this one. I'm going to go back to my pot. I'm going to make me a pot of soup, which is, yeah, you know, hey, it's a pot. And in this pot of soup, we're going to have some currents. What direction does warm go? Warm goes up. Warm goes up. Cool goes down. If you've ever watched soup boiling on the stove, or if you made ramen on the stove, you can see all your little tidbits and stuff. So I'm going to put some carrots in there because, like, even ramen has little pieces of carrot. And some peas. But you can see the water moving, and that water moving in boiling water is caused by these convection currents, and these convection currents are caused by the pan being warmed. Well, I'm gonna do gas stove. I'm gonna do a gas stove. So this is some fire underneath it. But boiling water, boiling is convection. Boiling is convection. Another example that they like to put on tests are these things. I can almost guarantee you when the district gives us our test this year that this is going to be on there. And it's these big things like this, and then they'll have this little basket hanging down off the bottom, and that little basket can have people in it, but above the little basket will be this thing, and this thing, when you pull the cord on it, makes a big jet of fire go into the balloon. And that big jet of fire warms the air in the balloon, and that warm air, what direction does warm go? The warm air rises. Warm rises. This is a hot air balloon, and that hot air balloon, this is exactly how they work. They're just filled with air. They're not filled with helium. They're not filled with anything except air. They heat up the air, and that air makes the balloon go up. Hey, ooh, hey, this is an opportunity for some review. energy transformations. Oh man, let's do it. All right, so the energy inside of propane, which is the gas they burn, the energy inside of propane is stored up as what form of energy? What form of energy? Is it chemical, mechanical, kinetic, potential, gravitational potential? This one goes chemical. When you burn that propane, what kind of energy is released and made? Or what kind of energy does the chemical energy turn into? It turns into thermal, which, remember, thermal is heat energy. And then that thermal energy gets transformed one more time as the balloon is rising, which that rising is movement. And we know that the energy of movement is kinetic, but specifically when things move, it is mechanical. So you have chemical energy transformed into thermal energy, transformed into mechanical energy. The energy inside the propane burns hot, which warms the balloon, which makes the balloon move up. That's mechanical. Last bit. Now, well, the last picture, and then we have a tiny bit to draw. So this last picture is wind. There's two different kinds of wind. There's two different terms specifically that deal with wind. So we're going to come down here, and I'm going to draw my little arrows. So wait, I need some ocean. I need some water. It'll make more sense with water first, and then over here I got my land. So this is the beach. This is the beach. Sandy beach, and then on the beach we need a little happy tree. So we need a tree because we're thinking tropical things, we're thinking warmer weather, happy things. And then we have our sun. It's not just a yellow dot, it is a sun. So put some sunglasses on my son and make him smile. Okay, so there we go. The sun is out. The sun is warming the water. And when the water warms, the air directly over the water will do what? The air directly over the water will rise. And it will go up. So I'm going to draw my little arrow to go up. As the air rises, it cools off, and as the air cools off, you can see this in the sky because clouds are places that warm air is rising, but that warm air starts to cool off. So that warm air, as it cools off, will turn. And we're redrawing this, but there's a reason, because the wind has special names. So it'll cool and travel sideways. And then once it completely cools, it will sink, the air will fall, the air will sink back down to the ocean. And then when it hits the ocean, that water is warm, so the air will turn, start to heat up again. And then rise. So this is normal. You know this. Here along the surface, along the ocean or the land, we would just call this horizontal, this sideways movement, wind. But when you get really high up in the atmosphere, really high up in the air, that wind is moving at hundreds of miles an hour. It is incredibly fast. And that wind we call the jet stream when it's that high up. It is a large, fast moving river of air. All right, this is our very last bit, so you have made it to the end. This is the most writing we're going to do, so let's go. Convection is all about mixing. So warm air, warm, air, water, or magma rises. Cool. Air, water, or magma sinks. And this movement, this mixing forms currents. So this makes currents. You don't have currents unless you have heat. You don't have currents unless you have different temperatures. If everything is the same temperature, it doesn't move. This makes currents. So there we are. We have done 2 pages of notes. Convection, radiation, and conduction. I like Doodle notes better than these notes, but these notes were also very key for you. So now you have 2 ways to refer to the same information. Like I said, thank you guys for coming in, ready for class, and taking care of business and getting these notes done. I will see y'all tomorrow.